3b. So last lesson you looked at compound angle formulae, which I have written on the board here for you. These were the 3 new identities that you know. I can't remember if it's in the formula book or not. I think it might be in the formula book. But along with the compound angle formulas, there's something called the double, Ruben, there's something called the double angle formulae. Okay, double angle formulae comes up quite a bit, probably more than compound. Although actually compound and double might come up at the same time together, and we'll look at some of those as well at some point. But basically, the first identity is what is sine 2x. Okay, so the way to consider what is sine 2x is to think of it as sine x plus x, where a is x and b is x. Okay, so when I replace in my double angle formulae a and b with x, you get sine x cos x plus or minus, well, plus because I've put plus in the middle there, plus sine x cos x. How can that be rewritten? Yeah, just 2 sine x cos x. So sine 2x is the same as 2 sine x cos x. Okay, so that's one of the identities you need to know. You don't have to know a negative one, because if you did x minus x, well, that's nothing. Okay, so that's sine 0. There's no negative version of this to be aware of. Sine 2x is the identity, and it's always 2 sine x cos x. Okay, let's have a look at what happens with cos 2x then. So again, cos 2x, treat it as cos x plus x, where a and b is x. You end up with cos x plus, minus, because it's plus is minus in cos, plus sine x. What does that simplify to? Cos squared x minus sine squared x. When it's plus in the bracket, it's minus in the expansion. Remember, plus minus that way round. If it's minus plus that way round, the top lines up with the top, bottom lines up with the bottom. Okay? Sorry, sine squared x. Sine squared x. Cos 2x actually has 2 other identities. Okay, other than cos squared x minus sine squared x, because you already have an identity involving sine squared x's and cos squared x's. You'll also know that cos squared x, let's do it properly. Sine squared x plus cos squared x is what? 1. Okay, so what they do is they do a rearrangement of this to say if sine squared x is 1 minus cos squared x, and cos squared x is 1 minus sine squared x, I can replace the cos squared x here with this, or I can replace the sine squared x there with this, giving me 2 other identities. Okay, so the 2 other identities become, is equal to, if I replace cos squared x, it becomes 1 minus sine squared x minus sine squared x, which is the same as 1 minus 2 sine squared x. So that's one of the other identities. Oh, wrong thing. So I'll just bracket these round. And the other one, will be equal to cos squared x minus 1 minus cos squared x, which becomes 2 cos squared x minus 1. Okay? So when you see cos 2x, there's actually 3 identities it could be. Either one of those 3s. Okay? Again, I think they give you all 3. They might not. They might do. But it's just using a combination of one identity with another identity to create multiple other identities. Okay? I think it's kind of pointless that they give you these 2 extra identities, because it should be something you should be expected to work out yourself, in my opinion, from just that cos squared x minus sine squared x. You should be able to generate these identities anyway. but I'm pretty sure they give you them in the formula book. Okay? So basically, when you see cos 2x, you need to decide which one of those three am I going to use. Because if you start using one, it can be a long day. Okay? I don't know how many times you've done trig identities and gone down the wrong rabbit hole, but I have spent at least half an hour on questions before realising, I could have just gone this way, and it's so much easier if I did it that way. Yeah. Lots of expansions, especially now that there's because these formulas, you get these massive expansions which slowly start to reduce towards the end, but sometimes you can actually skip some of that large expansion and things disappear a lot quicker if you are able to think about it in a certain way. It's not fun. But it is fun. Again, tan 2x, same idea, treat it as tan x plus x, where a and b is x, giving you tan x plus tan x, which is just 2, let's write it out in full. Tan x, capital, tan x plus tan x over 1 minus tan x, which is just 2 tan x over 1 minus tan squared x. Okay? And I'm pretty sure that's the only identity they give you for tan 2x off the top of my head. Yeah, that's it. So, if you know your compound angle formulas, you can generate these double angle formulas, but you don't need to. I'm pretty sure they give you all of these ones as well, but the only reason they exist is by what I've shown you here, the proofs. These are the proofs for these identities. It's in the book as well, if you look it up. And then similar ideas that we were covering yesterday. I don't want to go through too many examples right now because there's not too much longer left. So if you want to start having a crack or maybe read through the examples yourself if you're unsure about anything. I don't think there's anything special that you've not really covered, other than maybe if you look at worked example 3.6c, that uses the expansion of tan x over 2, okay, where they consider what the expansion of tan x would be, and then replace x with x over 2 at the end. Oh no, we didn't do that. Oh, all right. Actually, guys, I'll do that one. Sorry. It says 3.6c. Says given that sine x equals minus 3 over 5, and that x is between 180 and 270. Oh, so guys, that's to answer some people's questions yesterday about the cast diagram. I was asked, how do you know which part of the reflex angle it would be, whether it would be in the tan side or the cos side, because reflex is between 180 and 360. They can define a region. So if they define the region 180 to 270, in terms of your cast diagram, you know you're going to be down that direction. Okay? And in that direction, whatever the theta is, the opposite will be minus 3, and the hypotenuse is 5. Okay? Because sine x is minus 3 over 5, so that's your opposite, that's your hypotenuse. Work out your adjacent using Pythagoras, yep.
So with theta, do we always make it with the x-axis?
Theta, yeah, is always the angle made against the x-axis. Okay? Never against the y-axis. Always the x. Okay? So that's why the other day I drew that kind of bow tie situation. Those are the angles that theta refers to. Okay. Anyway, so you'd work out the other side, the adjacent side, is minus 4 by using Pythagoras. It would be the magnitudinal value of 4, but because it's on that negative part of the coordinates, it's minus 4. Okay, that tells you that tan x would be equal to minus 3 over minus 4, which is just 3 over 4. And if you remember cast, we are in that tan region, so we know tan should be a positive value. Okay, so that's why it becomes a positive value. Cool? Nice. All right, so tan x is 3 over 4. However, it says find the exact value of tan x over 2. So, what they've done is they've considered x as 2a. Okay? They've considered x as 2a. So, basically, instead of me saying sine 2x, they're saying sine 2a, or tan 2a. Okay, maybe this is why they've used a in the book, but it's the same idea. So it's 2 tan a over tan squared a. Okay, so if you consider x is 2a, that means that I can replace in my 2 tan a over 1 minus tan squared a. I can say that a is equal to x over 2, and then replace this in here. So you end up with 2 tan x over 2, 1 minus tan squared x over 2. That's the same as tan x. And they do that quite a bit. Like, that's not the first or last time you'll see them do that. Okay, so it's not always going to be that they've actually applied a multiplier to the x here. It's not always going to be tan 2x. Sometimes they're going to give you tan x, and you've got to realise, well, if x is 2a, or x is 2a, then a is equal to x over 2, and you put it into that identity as x over 2. Okay? Or they could have that with a different number, potentially. If it was x over 4, you'd use x... Sorry, if it was x over 2, you'd use x over 4, because 2a would be x over 4. And that's probably, again, like I say, why they've said in the book, rather than x, they've called it a, because quite often the x value that's given is not x, it's... If that makes sense. Like with our binomial expansion, you know how it was always like, oh, you use the x and then the x squared and then the x cubed, but sometimes x would be actually x over 2. They should really be using a, maybe, to differentiate between the input and the output. Maybe. I'm confusing people now. But I wasn't going to worry myself too much. Okay, so once you've got to this stage, you know what tan x is. So you'd say 2 tan x over 2, 1 minus tan squared x over 2 is equal to 3 over 4, because tan x is 3 over 4. Okay, and then it becomes a quadratic, so you get 2 tan x over 2 is equal to, 8 tan x. I'm just going to times up by the 4. I'm going to times up by 3 minus 3 tan squared x over 2. Everyone okay with that? Time cross multiply, get it all to one side, so 3 tan squared x over 2 plus 4 tan x over 2 minus 3 equals 0. Treat tan squared x over 2 as u. Okay. I did have it as 8, and then I crossed it out to rewrite it, and then I forgot to write it as 8. Thank you. Right. So I can treat this as 3u squared plus 8u minus 3. So 3u squared plus 8u minus 3 equals 0, giving me double brackets equals 0, 3u u plus 3 minus 1, plus 3 minus 1. Okay, so 3 tan squared x over 2 equals 1, or minus 1 equals 0. And tan squared x over 2 is equal to negative 3. That's not going to give you a solution. Why is it not going to give you a solution? Because you would be square rooting a negative number. But am I being stupid? Yeah, I am being stupid. Thank you. Yeah, because my substitution was tan x over 2 equals u, not tan squared. Yeah. Okay. Sorry, that was me being stupid. So I should have got tan x over 2 equals minus 3, which is solvable. Okay? So inverse tan that to get x over 2 is equal to the inverse tan of this. Do that on a calculator, then times it by 2 to find x. I don't have a calculator, but it gives you the answer of x as... Oh! What? Sure about x over 2? Oh, yeah, right, actually, yeah. What? Yeah, sorry. So actually we've got two solutions here. We end up with this being tan x over 2 equals 1. Tan x over 2 equals a third. Okay? But only one of those solutions would work. Okay? It says if 180 degrees is less on x than 270, then 90 degrees x over 2 between 135, which means... I don't even know what it's trying to say. Oh, yeah. Okay. So, if x is between the value of 180 and 270, then x over 2 will be between values of 90 and 135. Okay? Cool? Is that alright?
Why 135?
Because it's half of 270. Okay? Okay. Right. Which means it's in this second quadrant region. Okay? Between 90 and 135 is in this region here, which is, in terms of my cast diagram, means that the solution of tan x over 2 must be negative, not positive. So that means the only solution is this negative solution. Okay, because this positive solution would be either in the tan region or the ol region. Okay? Is that okay? That's quite a hard part of it. A lot of that is hard. You what? Yeah, go on.
Wait, so can you explain that?
Yeah, because 3 tan x over 2 minus 1 equals 0. Tan x over 2 is a third. There's two solutions. These are the two solutions, but the actual solution is that one. This one does not work. That's what I was just saying. Because we know it's in the region 90 to 135, which means tan x over 2 must be a negative solution.
So, can you explain why it's between 90 and 135 again?
Because in the question it tells you that x is between 180 and 270, so x over 2 will be between 135 and 90. Yeah? Cool. Any more questions? Any more questions about that one?
How do you do it without the cast diagram? Because you don't know how to use it.
How do you do it without a cast diagram? You, again, identify it's between 90 and 135, which means that in terms of your value, that's 135 there, that's 90 there. You know there must be a negative solution because it's in this region. You are in that region. So you know there's going to be a negative solution, not a positive solution. Is that okay? The book prefers cast, it seems. But all cast... Guys, so with cast, I generally dislike it for when we look at talking about multiple solutions. Okay? When we're talking about multiple solutions, like we were 2 lessons ago, I prefer the diagram because I can see way easily where all my multiple solutions will be, and I can work it out using just the symmetrical rotational nature of these diagrams. But when it comes to this stuff, I actually think cast is quite useful. Just for this whole, if sine x is minus 3 over 5, what must my adjacent side be? That is it a negative or positive value? That side of things. For those exact value solutions, I think it's quite useful. Okay? It tells you what region you're in for these kind of questions, so that's why you don't really need to know about the multiple solutions, because you're only in one region anyway, and that one region is generally only one solution. Okay? because you're either between 0, 90, 90, 180, 180, 270, and 270, 360. You're in one of those regions, okay? And in every diagram, there's only one solution within each of those regions. With basic sine x, cos x, tan x, anyway.
Sure.
Cool. I'm happy to do more of these questions.